All right, sorry about my lateness. Of course, today there's a screen issue, but anyway, we'll finish up SN1. So this is Savolysis reactions, and there's, again, two complicating factors of this due to the nature of the intermediate, which forms a carbocation. So we'll look at those structures, we'll push some arrows through the mechanism, and we'll talk about racemization as well. And so your exam for this module will open today at 12:15. You'll have the 24 hours to do it. And don't forget to hit submit when you're done. Any questions before we get started? So we had left off talking about the characteristics of the SN1, and for the most part, a lot of the factors are kind of opposite that of SN2. So again, the trend is tertiary substrates react faster than secondary, and then primary and methyls we don't have to worry about unless they're allylic or benzylic, which we'll talk about those structures again as well. So solvents for SN1 are polar and are now protic. So protic means, in general, OH functional groups and NH. For our purposes, really, we're just focused on the OH, which we know are alcohols and carboxylic acids. The polar part, again, you determine that from a difference in electronegativity between the two elements of the bond. So you're looking at, the periodic table running from CNOF. So that change in electronegativity, that determines the polarity. The protic part is going to either be an alcohol or a carboxylic acid. So of the 5 solvents listed here, from left to right, they are increasing in dielectric constant. I'll explain what that means in regards to the mechanism, why that's important, but you can see that we have acetic acid, so that's ethanoic acid. The common name is acetic acid, ethanol, methanol, formic acid, and then water. So water has the highest dielectric constant. But the two main classes are carboxylic acids and alcohols. That's what we're going to use. The other thing to note about SN2 versus SN1, the solvent what's going on here? The solvent is also the nucleophile. So when you're looking at reaction conditions and you don't see that other reagent, that strong nucleophile, you just see solvent, chances are it's going to be an SN1 reaction. So after we get done with this module and we move into module 5, there's another type of mechanism called elimination, and things can get a little murkier there. But overall, the reagents above the arrow, that's telling you what type of mechanism is going to be there. So you have to recognize strong nucleophiles, solvents, and then for module 5, you have to recognize bases. And so ultimately, the difference between substitution and elimination would be the presence of a base. So why do we use protic solvents now? Why are protic solvents carboxylic acids and alcohols important for the SN1 mechanism. We know that, given our tertiary bromide, we have that polar bond, so CBr, where Br is the leaving group. That's a polarized bond, so that's the bond dipole. With a protic solvent, that hydrogen is typically delta positive. So due to the change in electronegativity between O and H. This dotted line here, so that signifies an electrostatic interaction between the delta plus and the delta minus. So what you can think of the H is sort of throwing a lasso around the bromine or the leaving group, and it's tugging on it. So as it tugs on that leaving group, it makes that carbon-bromine or carbon-leaving group bond weaker. And due to my limitations in drawing this stuff and just visualizing it in general, I'm just showing you one solvent molecule. But you imagine the bromine's a big ball. It's surrounded by these solvent molecules. So all of them are tugging on that leaving group. And that tug helps to ionize. That's the rate-limiting step in SN1. So we know that that bond is going to cleave. So that's the ionization. So the more polar and protic, the higher that dielectric constant is, the more it's able to pull that leaving group away. And then ultimately what it does is help to stabilize that leaving group. So imagine it's surrounded by or solvated by those solvent molecules. So again, solvent is what we run the reactions in. It's typically a liquid. In terms of the molar ratio, you have a lot of solvent molecules per every one molecule of your substrate. So it's there in high concentration. Therefore, competitively, it acts as the nucleophile as well. So at this point, the carbocation that's an electrophile. And the solvent, which is going to supply electrons, is a nucleophile. So this is a Lewis acid. The solvent is therefore a Lewis base. It's supplying electrons. So the substrate gets ionized, it forms a carbocation. What is the stability trend for carbocations? Why does this mechanism prefer tertiary? And why do primary substrates not react? So allylic and benzylic were the special cases we need to review, but overall the trend is tertiary substrates react faster than secondary, and the primaries do not undergo this mechanism. The secondary ones are really the substrates that you have to diagnose the conditions to determine does it go SN2 or SN1, because that's where the overlap of those two trends are. So again, they run in opposite directions, but you see that secondaries are both in the middle. So to determine if it goes SN2 versus SN1, you're looking for the presence or the absence of that strong nucleophile. Is there anything else in there that's funneling it one way or the other? So why does that matter? What mechanism the substitution happens by? Remember the stereochemical issue. SN2 goes with complete inversion, and SN1 will go with racemization. So the conditions will determine ultimately the stereochemistry, the stereochemical outcome. So when the carbon atom that's bonded to the leaving group, in the starting material, it's sp3 hybridized. The leaving group leaves, it's ionized, the hybridization changes to sp2. And the positive charge resides in the p orbital. So in general, say for any carbon atom, whatever those three substituents are, there's that p orbital. So it's empty. That makes it the Lewis acid. It can accept a lone pair to form the new bond and then rehybridize to sp3. Why does it follow the trend? Tertiary is greater than secondary, greater than primary. Let's first look at the allylic and benzylic cases in terms of the rate. Those will always react fastest due to additional stabilization. And that's from resonance. So here we have, I'll just draw the structure of this. So there's that structure. Then below it, I'm showing the p orbitals of the double bond. This is a primary allylic bromide. So even though it's primary, the fact that it's allylic, that will increase the rate, and it can undergo SN1. When this ionizes, the blue is the p orbital, and then these gray, that's the two p orbitals of that double bond. So in that double bond, remember there's a set of electrons. That carbocation can be stabilized if those electrons hop over, and then that empty orbital migrates to the third atom of that unit. So if we number these, so 1, 2, and 3, 1, 2, and 3. The electrons move over. We see the plus charge primarily resides at the 1 and the 3 positions. So the fact that it's stabilized helps it ionize easier. So the important thing to remember or spot is knowing what the term allylic means. Benzylic, is this sp3 hybridized carbon atom that's bonded to a benzene ring. Notice it's not in the ring itself. It's the carbon atom that's next door, and it's sp3 hybridized. So that's called benzylic. The same resonance stabilization can happen with benzylic substrates. So this bond ionizes. That carbon atom is now sp2 hybridized. So that's indicated by the blue p orbital. So we see it up here. It's outside the ring. Then if we number 1, 2, 3, 1, 2, 3, you can see that it's now delocalized into the ring. There's those 2 other double bonds, so it can migrate over 2 more times. So this structure would look like this. The structure below it would look like that. And then the last structure would look like that. So overall, you have these 4 resonance forms where that plus charge it's located at very specific positions. Alternatively, you can think about it, where is it not located? If you go on to take organic 2, these resonance forms are very important in helping you predict exactly where reactions occur. So the allylic and benzylic, even though if your substrates are primary, they can still undergo SN1 due to the resonance delocalization. But in general, how do we understand the trend of tertiary greater than secondary greater than primary? We're going to look at the nature of the sp2 hybridized carbon and then those 3 things bonded to it. So we can explain this in 2 ways. The first way is called induction. Induction is best described as through a sigma bond. And what we're looking at here, I'm going to draw this slightly different. So here's our sp2 hybridized carbon. We have these 3 bonds coming off it. We have the p orbital. Now imagine putting your eyeball either above or below. And then what you're looking at here is the top of that p orbital looking down, that axis. So when we look down, we can see that for a tertiary substrate, say if we have methyl, methyl, and methyl, the bonds highlighted in red, those methyl groups are pushing electron density through those sigma bonds into the p orbital. So that's a stabilizing factor. Because a carbocation is a reactive intermediate, again, relative to where you started, it's higher energy. If it's higher energy, it's reactive. If you can stabilize it in any way, it's going to be easier to form. So as we go from tertiary to secondary, we remove a carbon, replace it with hydrogen. Notice that bond is no longer colored red. It doesn't have the same stabilizing factor. And as you successively remove carbons from it, the stability of that decreases. So if stability decreases, that means the reactivity increases. It's higher, much higher in energy. It's harder to form. So induction is maybe a basic way of understanding that. This next term is more commonly used, and that's called hyperconjugation. So now, what does that mean? So for induction, remember, we were looking down the axis of the p orbital. Now we're going to look orthogonal to it, or 90 degrees. So we're going to put our eyeball in line with that carbon there and look down that axis. So now we see both lobes of the p orbital. So there's the front carbon. It's a methyl group, so we have H, H, and H. The back carbon, there's the p lobe, or the p orbital, both lobes. We know that sigma bonds can rotate. So if we have a CH bond that's directly aligned with either lobe of the p orbital, the electron density in that CH bond can stabilize the empty p orbital through space. So up here I said through bond. This interaction is through space. So you can imagine that you have 1, 2, 3 methyl groups. They can each align with those lobes. So that's increased stabilization. As you remove each carbon group, then you go to hydrogen. So right here. That hydrogen can't align the same way. Now, in terms of a dihedral angle, that would be 0. So when you get to, what is this? Tertiary, secondary, no, primary, you only get one of them. And then methyl group, that's not possible. You can't have any of those alignments. So for SN1, primaries and methyl groups are not good substrates. Any questions? So my throat's still a bit scratchy today. So this next complicating factor of SN1, again, in the mechanism, it's going to require that you can't just get to the answer. You have to go through the mechanism and then ask these questions. So in this algorithm, this is going to determine if the substitution happens where the leaving group originated, or if a rearrangement occurs and the substitution happens at another carbon. So with carbocations, once they're formed, you always have to go back to that stability trend. Is this the most stable carbocation there can be? So carbocations can undergo rearrangement. So remember, the trend was Tertiary is more stable than secondary, much more stable than primary. So to determine if this will happen, all of the substituents bonded to the carbocation must be evaluated. So say we have a carbon bearing a leaving group. I'm going to refer to that as the alpha carbon. And then the next carbon is the beta carbon. But that can sprout off into 3 different paths. So once the leaving group leaves, it generates a carbocation and you classify it. Then you say, is that the most stable carbocation that can form, yes or no? If yes, then the substitution is going to proceed as normal. If not, you have to look at those beta carbons, and then 2 types of rearrangements can occur, and we'll look at those today. So of the 2 types, they're called hydride or methyl, and I'll generalize that methyl to alkyl. So from the beta carbon, something's going to move over to that original alpha carbon. And it will only happen if you can generate a more stable carbocation. So for example, if you originally start with a leaving group that's secondary, then you evaluate the beta carbons and you say, hey, look, if I move this group over, the new carbocation will be tertiary. That will happen because it's more stable. And now the substitution is not occurring at the original carbon bearing the leaving group. So to understand that, let's look at 2 examples here, and we'll walk through the mechanism. So we're going to start with, what's the name of this thing? We have 5 carbons, so it's a pentane derivative. At carbon 2, we have an alcohol, so it's a pentanol. And then carbon 3, we have a methyl group, so this would be called 3-methyl-2-pentanol. Remember we said in SN2 reactions, you could not substitute a hydroxyl group because it's a bad leaving group. Under SN1, we're going to use methanol as the solvent, and then we're going to have a catalytic amount of acid. The acid's going to transform the alcohol into a good leaving group. It's going to leave. And then the solvent is going to do the substitution. So I've shown you the starting material and the product. And what do you notice about the product? So where is the alcohol located in the starting material? Huh? So it's located at position 2. And then where do you notice in the product where the solvent is bonded? So carbon 3. So how do we explain that? The leaving group is leaving from carbon 2, but the substitution is occurring at carbon 3. The other thing to note, in the starting material, carbon-3 has an H there, right? There's also a single H on carbon-2, but in the product, carbon-2 has 2 hydrogens. Carbon-3 no longer has the hydrogen, and it has the solvent molecule O-methyl, so now it's an ether. So if the leaving group's departing from carbon-2, how does it get substituted on carbon-3? What's happening? So under acidic conditions in solvent, the hydroxyl group can ionize through this oxonium ion intermediate that forms a carbocation that we then have to evaluate. So what's our mechanism here? I'm going to stick those hydrogens in just so we can keep track of them. Normally I wouldn't show them because they're bonded to carbon. We're treating with hydronium H3O+, in methanol. So a secondary alcohol is now going to an ether. We need to get rid of that OH group, but it can't just ionize, because if it leaves as it leaves now, then it's hydroxide, right? Hydroxide is OH minus. We're under acidic conditions. So we have to protonate using hydronium ion. So that's an acid-base reaction. So O+, that's oxonium. Now that can leave. That's going to ionize. When it leaves as water. That's fine. It's neutral. When we classify that carbocation, so remember that's our alpha carbon. It was bearing the leaving group. How many carbon atoms are attached to that alpha carbon? So this alpha carbon is bearing 2 carbons, so that's a secondary carbocation. And we know that secondary carbocations are not the most stable, right? Because tertiary is the most stable. And then we look at those 2 carbons, so that's beta, and then this other one's beta. That beta carbon has 3 hydrogens. I just drew 1 in. If we were to shift that hydrogen over and then the plus charge moves up to that beta carbon, what would the class of that carbocation be? That would be primary. That would go down in stability, right? So we wouldn't want to do that. When we look at this beta carbon, if we move this hydrogen over here, the class of that new carbocation is what? Tertiary. So secondary can rearrange to tertiary because it's more stable. The reason it's called a hydride migration the electrons in this carbon H bond, those electrons move over. Then that plus charge has to migrate to where it was bonded to. And so now that forms a tertiary carbocation. That's allowed because it's more stable. And that's called a 1,2 hydride shift. So since we formed a new carbocation, that's now the alpha carbon. And for the purposes of this class, you can only do that once. You form something more stable. At this point, you do not have to reevaluate those new beta carbons. So now there it's a stable intermediate. The methanol is the solvent. It's the weak nucleophile. It will attack that carbon. That forms a new oxonium ion, and then that undergoes an acid-base reaction. So we can have water do a proton transfer. And that's how we end up with our ether. So again, it's important to, as you're writing these things, classify what are you starting with in terms of a leaving group. We started with a secondary alcohol. It was protonated, then ionized and water left. That generates a secondary carbocation. From there, we had to evaluate the beta carbons to see if a rearrangement could occur to something more stable. We found that one of them could. That underwent the 1,2 hydride shift to a tertiary carbocation. That's the electrophile. It's trapped by the solvent, and then following the proton transfer, we end up with our ether. So again, when you look through these, you're reading your textbook, doing problems, pay attention to the hydrogens bonded to what carbon, are things moving over. You see that carbon 2 in the product has a CH2 group where it only started with one CH. Any questions? So this next run of slides just sort of reviews those individual steps. Upon protonation of the hydroxyl group at C2, the C2 carbon oxygen bond will ionize to form what type of carbocation? So again, under acidic conditions, we have to protonate. That makes the hydroxyl group into the oxonium, which is a better leaving group. So when that ionizes, that gives us the secondary carbocation. And we look at that carbon, count the number of carbons to it, 1, 2. That gets us a secondary. Upon ionization, a secondary carbocation is formed at that alpha position. Carbons directly bonded to the alpha carbon are designated beta. How many unique type of beta carbons are there? So that's a carbon, we can call that beta. That's a carbon, we can call that beta prime. They're different, so there's 2 unique types. So that's the question that you have to answer for all of these mechanisms is looking at those beta carbons. Are they unique? And then can you do some sort of shift to form a more stable carbocation? And that explains why you can't just memorize an answer for this. So of the 2 unique beta carbons, what are their classifications? So that one is primary. That one is tertiary. And you figure that out by just looking at the number of carbons bonded to each of them. So we end up with B, primary and tertiary. And once you do that, it's really going to tell you if a rearrangement can occur, because we started with something that's secondary. We see that by classifying, one of them became tertiary. That's going to show us it's the driving force for a rearrangement. So primary, tertiary. Following that stability trend, tertiary greater than secondary, greater than primary, will the system undergo a rearrangement? The answer is yes, because a secondary carbocation can rearrange to a tertiary one that's more stable. So again, to repeat, that plus charge has to move over 1 carbon atom. So we call that a 1-2 shift. The electrons in the CH bond move over, so that forms a new CH. And the consequence of that is that beta carbon now gets the plus charge. So we can classify that as a tertiary carbocation. Now there's nothing else it can do. That's the most stable thing. Again, for the purposes of this class, the reason why you don't further evaluate a tertiary will not go to another tertiary. If that number's the same, that's called a degenerate. Degenerate means the same. You already formed something that's stable. It's not going to undergo another rearrangement to a tertiary. So it has to be a driving force to form something that's more stable. So it says, when that tertiary intermediate is trapped by methanol, does the final product contain a stereogenic center? So that's the nucleophile trapping the carbocation. So I'll say that, then proton transfer. So that's the final product. And does that contain a stereogenic carbon? See some no's, so the answer is no. The reason for that, this carbon has O-methyl, methyl, and then these ethyl groups here and there are the same. Since they're the same, they're not four unique type of groups. So even though it's drawn with a bond rotation, just recognize that those are the same thing. Questions? Let's look at another example. In this case, the rearrangement is not hydride, but it's methyl. So methyl is exactly that, CH3. That's going to be the group that moves. It's not going to be H. I do want you to keep in mind this can be generalized to alkyl. And think about everything that you've learned up into this point in the course. You know, the physical organic chemistry stuff from Module 3 about strain. Part of the thing that drives rearrangement is the release of strain. So we have a secondary iodide. Our solvent is ethanol. Notice there's no other strong nucleophile present. So the solvent and the nucleophile are the same thing. The ethanol gets incorporated into the molecule there. And then what else do you notice about the starting material versus the product? See these two methyl groups? Let me redo these colors here. So I want to leave a blue one on that carbon, and then I want to make that one green. So in the starting material, they're both blue because they're bonded to the same carbon. Then in the product, the blue one's retained, and then one's highlighted green because it moved over. And where did it move over to? Where the iodide was. So let's walk through this mechanism. So again, we can see that we're starting with a secondary iodide. In the product now, there's a methyl group where that iodide was. In the starting material, that carbon has 2 methyl groups. Now it only has 1, and now we have the elements from the solvent. So these are SN1 conditions, weak nucleophile, which is the solvent. The leaving group gets ionized. So minus H minus. And then what is the class of that carbocation? So I've designated it the alpha carbon. We count the number of carbons bonded to it, 1 and 2, so that's a secondary carbocation. Now we have to look at those 2 carbons, so beta and beta prime. And then we have to consider, can something move to make that secondary carbocation more stable? From beta, we have 2 hydrogens. If one of them moves over, what is the class of that carbocation that forms? It'll be secondary. So secondary to secondary is not allowed because you're not gaining any stability. So I'll draw this in, I'll draw it in blue going that way with an arrow through it, which means it doesn't happen. So if that migrates over, it forms that. We can classify that as secondary. So you're not gaining anything by doing that. If we look at beta prime, we can see that beta prime has 2 methyl groups. Now one of them can migrate over. Then we can classify that as a tertiary carbocation. So we've gained stability. That's allowed. That's called a 1,2 methyl shift. So now the solvent can attack that. That generates the oxonium ion. And then we can do an acid-base proton transfer. So in general, under the SN1 reaction, if you're starting with alcohol as your solvent, you're going to end up with an ether as your product. A carboxylic acid solvent will generate an ester as your product. And again, that's because those things are the nucleophilic component.
Questions? So that's the rearrangement aspect. The next aspect of this is if you're starting with a stereogenic carbon, what happens in terms of the stereochemical result of the reaction. So whereas SN2 gave you complete inversion, SN1 gives you racemization. And that is because the nature of that carbocation intermediate. So if the carbon bearing the leaving group Lg is a stereogenic center, that RRS stereochemistry is lost because of that rehybridization. So sp3 goes to sp2. That's because the p orbital has the plus charge. We said the p orbital is dumbbell shaped. It has two lobes above and below the plane. So C, there's our carbon. It's trigonal planar. There's the p orbital. You have the top and the bottom lobes. The nucleophile can attack either of those equally. So if you're starting with a stereogenic center, the information's lost. The nucleophile can attack from above and below. That results in racemization. So racemization is a production of a one-to-one mixture of the R to S stereochemistry now. The example shown here is a tertiary bromide. We can see that that carbon has 4 unique substituents: bromine, methyl, ethyl, and propyl side chains. It's ionized, so sp3 now to sp2. There's the p orbital. Our nucleophile is water. Water can attack from either the left or the right, top or the bottom, however you're looking at it. So you can end up with the retention, but also the inversion. So that's a one-to-one mixture of those two things. That's called a racemic mixture. So the one-to-one mixture of R to S, if you take those product alcohols, you put them in a polarimeter, the optical rotation is going to be 0. So the instrumental technique, actually helps us understand that this mechanism is different. So the fact that it ends up 0 means that the SN1 mechanism has to proceed through this intermediate that is unique to the unimolecular kinetics. So based on all of this information, which of the following best fits the properties required for an SN1 reaction to be successful? So what are the kinetics? What's the best solvent? And then what's the nucleophile strength? So SN1, the 1 means unimolecular, so A and D are out. The best solvent for it, we wanted a protic solvent, so C is out. And then we want a weak nucleophile. So B is the best answer. So take a look at these 4 alcohols. If they're treated under SN1 conditions, so acid plus solvent, which one will ionize the fastest to a carbocation? What'd you say? D. So D is the correct answer. To get to that, let's ask this question first. One of them can be eliminated right away. And remember, the litmus test for either SN2 or SN1 is the carbon bearing the leaving group has to be sp3 hybridized. That's sp2 hybridized, so that's out. B, C, and D, those are all sp3 hybridized carbons. The next thing we're going to do is classify the leaving group. So they're all alcohols. What class are they? This is secondary allylic. This is secondary. This is tertiary allylic. So C is out because we have 2 allylics. Then among those, the tertiary allylic is going to react faster than the secondary. So again, when you're diagnosing these starting materials, that classification is important because it's going to help you quite a bit, in determining what's the nature of the class of carbocation you're forming. Is there resonance? Does it rearrange? Ultimately, where does the substitution happen? So we already answered this one. Which of the following will not undergo protonation and ionization? So not, and again, it's that one. So we have a minute or two, I can explain this. If that alcohol is protonated, so it forms that. Why does it not behave the same? If that were to ionize, the orbital that's left over, that is an sp2 orbital. It's not a p orbital. So that plus charge would reside in an sp2. That's much, much higher in energy. So when you're analyzing this, and this is where a lot of students get confused about these orbitals and bonds, even though it's crappily drawn here, see that double line right there? The p orbital for that carbon is already tied up in that double bond. So you're actually here cleaving a CsP2O bond. And that means that the plus charge has to still reside in an sp2 hybrid orbital. It's not in the p orbital because that, again, that's tied up in the pi bond of the ring already. So if 2-methylbutane were subjected to radical bromination, in the major product of that, treated with ethanol and heat, which of the following would be the final product? So this is like you're used to eating at Chick-fil-A, now you're eating at a Michelin star restaurant. You have to put a little finesse on the analysis here. So how do you go about thinking about this? We know that 2-methylbutane, there's going to be 4 unique sets of hydrogen. So these methyls are 1, 2, 3, and 4 unique sets. The ratios 6 to 3 to 2 to 1. So 6, 3, 2, and 1. Then what I'll do in blue, I'll just classify them. So we have primaries, secondary, tertiary. Remember, radical bromination is selective for what type of substitution? So of those sets, primary, secondary, tertiary, bromination prefers to substitute what class of hydrogen? Tertiary. So that tertiary hydrogen gets substituted. So bromine's selective for tertiary. We now have a tertiary bromide. These are SN1 conditions. Because it's already tertiary, when it ionizes, it forms a tertiary carbocation. So we don't have to worry about rearrangements. The solvent will attack where that is, and we'll end up with B as the correct response. So this is an example that illustrates how these different mechanisms allow you to take something that's non-polar, like 2-methylbutane. You only have carbon-carbon, carbon-hydrogen bonds. Through a radical CH substitution, you're introducing a halogen, which is a good leaving group. And then through this other mechanism, you're substituting that for a new functional group. So ultimately, you go from an alkane to a haloalkane, and now to an ether. And due to all the constraints we've learned, even though you're starting with four different sets of hydrogen, you can specifically substitute at one of them. So which of the following carbocations will undergo a 1,2 hydride shift? Someone said D. It's not correct. So again, this is where students trip up. that carbon atom is sp2 hybridized. That means the plus charge is residing in an sp2 hybrid orbital. So immediately that thing's crazy unstable. When you look at the rest of them, the carbons are sp2, but the positive charge is in a p orbital. So let's just classify them. We have primary, secondary allylic. Now the question we're asking is, can one of these things rearrange to form something more stable? So if we focus on the primary, if that's the alpha carbon, there's only one beta carbon. Now, if that rearranges, now it forms something that's tertiary and allylic. So A would be the best answer for this. B, you can't do anything. It doesn't matter what you look next to in terms of the beta carbon. If you do a shift, you still end up with secondary. So that, again, was degenerate. C is already allylic, so it has allylic stabilization. It's not going to do a migration because it can't form anything more stable than what it is. I think we have a quick summary slide here, go maybe a minute over. So now this fills in the two different mechanisms from SN2 to SN1. The blue colored rows are the promoting factors, and the purple are the characteristics. Really what you want to pay attention to, the stereochemistry is important. So SN2 was inversion, SN1 was racemization. And then SN1, again, you hit that decision point. Can this thing rearrange to form a more stable carbocation? But in general, the other factors in light blue run sort of opposite to one another from SN2 to SN1. The starting substrate trend, the solvent trend, polar aprotic versus polar protic in terms of how they promote the mechanism. So that's the last slide. Again, your exam is now open. You have 24 hours to do that, 30 questions, a couple bonus questions at the end.